During this the lecture sessions under dynamic inventory problems under certainty, I am going to discuss three issues. The first one is EOQ. So already we have developed the EOQ with the model. So we will be discussing on some different the characteristics of EOQ model, and particularly we will be referring to the optimal total cost. So how to determine the optimal total cost, and what are the the characteristic features of the optimal total cost, how EOQ is affecting the value of the total cost, particularly the total variable cost. Then the next important issue we are going to discuss, that how to determine the economic production quantity. That means it is a self-supply case. You need to produce certain amount with your own say the production unit and for the given inventory item. So how to determine the economic production quantity is a self-supply case, and of course we will be discussing or we will be referring to a number of numerical examples. Now, continuing our discussions on EOQ, already we have derived the EOQ formula, that is Q star equals to root over twice SC0 by ICU. Now, this particular the EOQ expression root over twice SCO by ICU can be expressed in different forms. It can be expressed in its equivalent economic order interval, particularly if you refer to the P systems of inventory control. As already you have pointed out, for the given inventory item, I can propose a Q systems of inventory control. I may also propose a P systems of inventory control. So if it is a Q systems of inventory control, I say that the order quantity is the EOQ model, assuming that all the 10 assumptions which we have already listed, all these 10 assumptions are valid. Alternatively, suppose it is a problem with certainty. That means the demand is known with certainty. You say that the P systems of inventory control needs to be followed for the same item. That is an alternative. So what you need to determine? You need to determine the order interval, and in this case this is referred to as the economic order interval. So obviously there is a relationship between the economic order quantity and economic order interval. So how to derive the expressions for economic order interval? Let order period T is in months. Like if you refer to that inventory profile, what you find that we have mentioned the order cycles. So the each order cycle is nothing but the order period. So suppose this order period is small t, and capital N is the total number of orders per year or the number of order cycles per year. Okay, so that means you count how many order cycles accommodated in a particular say the year or year's time, the 12 months time. So you find that there are capital N number of say the order cycles per year. So hence the order period is nothing but 12 by n months. If say if the order period, the measuring unit, if it is month, so that's why capital N is equals to 12 by T. Now N is S by Q. S is the yearly demand and Q is the order quantity. So hence Q equals to S by N. Now N is substituted with say ST by 12. That means S by N equals to ST by 12. If the 12 by T, N is equals to 12 by T. So that's why Q is nothing but ST by 12. If time period is expressed in weeks, and we assume there are 52 weeks in a year, so the Q will be S by N, that is ST divided by 52. Okay, so So ST, it will be, if you write ST by 12, this is the time period is in month, but if you write ST by 52, that means the order period is in weeks, and we are assuming that there are 52 weeks in a year. So what is the total variable cost expression? So that is TC equals to order, the cost per order, and how many orders you have, that is 12 by T per year. Is it okay? So that's why it is CO into 12 by T plus the inventory carrying cost, that means I into CU by 2 into Q. So what is Q? Q is ST by 12. Okay, so on simplifications, what you get this expression 12 by T into CO plus I into CU into S into T by 24. Once this expression is known, what you try to do, that means you try to minimize, minimize the total variable cost, and for minimization condition, what you have, that the partial derivative with respect to T of say TC is set to 0, and we get the economic order interval as TO equals to root over 288 CO by ICUS. So this is another expression of the equivalent EOQ, that is referred to as the economic order interval, root over 288 CO by ICUS. So all these parameters we have explained, what is I, what is CU, what is S, and what is CO. Okay. Now referring to the original EOQ formula with its total cost curve, we have already shown to you the total cost curve. We find that the total cost is very insensitive with small change in the value of each of the EOQ parameters around the economic order quantity, that is the Q star. So with Q equals to root over twice S C0 by ICU, this is the original EOQ formula, the optimal total variable cost EO, optimal total variable cost, is derived as the total variable cost EO is equals to S by Q, S by Q into CO plus I into Q by 2 into CO. Now this is the replaced with, that means the Q is replaced with Q star, that is root over twice S C0 by ICU. So when you substitute this expression of Q in this particular say the equation, what you find, that the total variable cost, optimal total variable cost, the notation is E subscript O, is root over twice S CO into ICU. Okay, root over twice S CO ICU. Okay, so this is the expressions we have. Now the sensitivity of the total cost with respect to the change in the value of one parameter, say CO. So what we have mentioned, that the total, say optimal, the total variable cost becomes highly insensitive to the change of say the parameter values. So what we have what we have assumed, that one such parameter is CO, that is the ordering cost per order. So so this is the expression for EO, root over twice S CO ICU. Now what you try to do, that means to verify its sensitivity with respect to CO, you take the partial derivative of EO with respect to CO. So this is the expressions you get when you get the partial derivative with respect to CO, and so what you get, that means the del CO of EO is equals to half into EO by CO. Okay, so in other words, del EO by EO, that means this is the proportion, equals to half of del CO by CO. That means supposing there is a change of 5% in CO, it will have say but the EO will be, that means the optimal the total cost will change by half of 5%, that means 2.5%, And this is true, this expression, this relationship is true not only with respect to CO, but this expression is true, or this relationship is true for all other, say, the parameters, all the other 3 parameters you have used in getting the EOQ, say, the formula. So, similar form of equation you may derive for each of the other parameters. It's clear? Now, for getting the total cost expression given CU and S, we need to estimate the value of CO and I. In many instances, that means CO is the ordering cost per order and I is the inventory carrying cost as a percentage or as a proportion of the average inventory which you hold. Now, in many instances, there may be errors in this estimation. It is quite likely. So, it is imperative that the error should be as minimum as possible, if not 0. That means whenever you deal with the parameters CO or I, obviously these are estimates, and make sure that these estimates are having the minimum error that is to be ensured. So, the key question is, what is the impact of this error on total cost? So, here is one derivation. Let us analyze this question in the following manner. Let actual values be I and CO. That means actual values of inventory carrying cost is I and ordering cost per order is CO. And the corresponding considered values, that means the estimated values is K1 into I, small k1 into I and small k2 into CO. Hence, actually we will be using these 2 values k1 into I and k2 into CO. Obviously, the order quantity which we will compute is given by 2s k2 CO by k1 I CU. Is it okay? Now, so the actual total cost based on Q. So, obviously you have a total cost expression, general expressions, and ultimately you get this expression. Okay, so my suggestion is so that you substitute all these values and you must check whether you are getting this expression or not. It's okay, so you try on your own. So, I am sure that if you follow the steps correctly, you will get these expressions. Now, the actual optimal total cost. So, these expressions already we have derived, that is root over twice as CO I CU. So, what is the difference? The difference is the delta, and capital delta is equals to this one. Is it all right? So, this is just you follow the steps, and this the difference as a proportion of the optimal the total variable cost as a proportion. That is why you form this ratio and you get these expressions. So, okay, half into root over k1 by k2 plus root over k2 by k1 minus 1. So, this is the expression. So, now you try with several values of possible values of k1 and k2, and there could be certain the conclusions you may draw, like if k1 by k2, that is the proportion, k1 is with respect to I and k2 is with respect to CO or the ordering cost per order. So, if this k1 by k2, this ratio is between 0.412 to 2.428, considered to be more or less a wide margin, what do you find? That this proportion, that means delta divided by the optimal total variable cost, will be always less than 10%. And if k1 by k2 lies between 0.5 and 2, then this proportion, okay, that means that difference with respect to as a proportion of that the optimal total variable cost will be just less than 6%. So with this analysis, we may conclude about the accuracy of the estimates, okay, and if any improved information system is needed for inventory management, because when you go for such estimates, you make sure that your information system is highly reliable. So it reflects when you go for this sort of analysis, so you'll have an idea that how as far as inventory management system is concerned, to what extent it gets the support of the company's information system, and you may also conclude the level of reliability of such an information system. Now let us talk about economic production quantity. Certain remarks I have mentioned. So let me first discuss those points. The EOQ model as presented is for an inventory item that is purchased from outside. Okay, so please follow these points. So the original EOQ formula, that means economic order quantity. So as soon as you use the term order, it means that it is an outside supply case. As soon as you use the term called purchase order, means that the item is to be procured from outside. So a purchase or replenishment order is placed with order quantity Q stated. You please refer to the flow chart or the flow diagram which we have drawn in respect of both Q system of inventory control and P systems of inventory control. But there are cases where there is no outside supply, but there is a self supply case. That means suppose one work unit using one inventory item, and this work unit needs a certain quantity of the item. So what it does, it places a work order to another work unit, say the machine shop or the fabrication shop or the assembly shop, and of course based on this work order, so that particular shop starts the producing it with the required quantity, and when the production is over, the required quantity is sent back to the work unit from where the work order has been placed. So however, for self supply, so this is called the self supply situation. However, for self supply situation, EOQ model is not applicable. Is it okay? So it is very clearly understood. So in a self supply situation, the item is being produced internally rather than procured from external supplier. So I have already explained to it. And when the production begins, a constant number of units are supposed to be added to the inventory each day till the time the production run is completed. That means against the quantity to be produced, that means so the production rate will be known, and once the production rate will be known, immediately you can calculate, you can estimate that how many what will be the time period, or how many days or how many weeks you require to produce the entire quantity. Okay, so this point is to be known. During the production run, the item is purchased at a rate referred to as the production rate. Actually, the item is produced at a rate referred to as a production rate. Simultaneously, the item is also demanded at a rate during the production run time. That means as soon as you start producing, okay, at a particular rate, you start using it. So what you have a production rate, and simultaneously you also have a consumption rate or the demand rate. Okay, so obviously the production rate has to be higher. Now this point is to be noted. That means the production rate has to be higher than the demand rate, and there is inventory build up. Otherwise it's not. Suppose you find that the production rate is less than the demand rate. So obviously it is say not a problem of inventory. So as soon as the production rate becomes higher than the demand rate, that means there is inventory build up. So and that's why it is referred to as one kind of inventory problem, for which the order the production quantity you need to determine optimally, and this production quantity is referred to as economic production quantity. Now this is the inventory profile, and this is for the EPQ model, economic production quantity model. So here what you find over here, so your required quantity is Q, and for which you have the production runtime, and the production runtime is TP. Okay, so depending on which type of say the production unit you use, so once the production rate is known, the runtime you can calculate. So at a production rate P, the inventory is supposed to pile up, but what is happening that you will never reach this point, because as you start producing at a rate P, you also start the consuming it. That means there is a demand, and this the demand rate is small d. So actually the inventory picks up in this manner at this rate. The rate is P minus D, and once the TP is over, that means you have the entire the production quantity produced, and subsequently you start consuming it, but at a demand rate of D. So here you find it is D. So this is the maximum inventory, and so this is one order cycle or the production cycle, and similarly such production cycles repeat. Is it okay? So this is your inventory profile. So please study this inventory profile, and I am sure that you will be able to understand all the critical points over here. Basically, you must know what is the production rate. You also must know what is the demand rate. You also you need to determine your decision variable is the production quantity, that is referred to as the Q, and for the given work unit or the production stage or the particular machine or machine tool, you must know that what is the production run length. Here the notation is TP. Okay. So now for each production run, for given production cost, the production system, say a machine, has to have a setup for which a setup cost is to be incurred. That means here instead of having the ordering cost, you have a setup cost. You must have an estimate of the setup cost. Usually the setup cost is estimated per setup basis. So let us assume that the Q is the total order quantity. You must get an expression for Q ultimately. The TP is the production runtime, P is the production rate, small p is the production rate, the small d is the demand rate or the consumption rate. Capital A is the setup cost per setup. So there must be a good estimate for this one, and H, small h, is the holding cost per unit per year. That means it is in absolute terms. That means once the the purchase per unit basis also you can calculate, and so once the price is known or the production cost is known, so first you go for the percentage, and then once the percentage is known and once the base price is known, you can calculate so the holding cost per unit basis and per year. Is it okay? So now the maximum inventory in the production cycle is given by, obviously you just refer to the inventory profile. So the maximum inventory is TP into P minus D, and the TP is Q by P. Is it okay? You just refer to the inventory profile. Hence the average inventory is half of the maximum inventory, half of Q by P. That means TP is replaced by Q by P over here into P minus D. This is P minus D. And so in further manipulation, what you find, Q by 2 into 1 minus D by P. So the total variable cost consists of the two types of cost. The first one is the setup cost and the second one is the holding cost. So the setup cost is given as, that means the setup cost per setup is capital A, and how many setups you have, that is capital D by Q. What is capital D? Capital D is the annual demand, and Q is the production quantity. So D by Q into A plus Q by 2 into 1 minus D by P is the average inventory, and you incur and holding cost of H per unit per year. So that's why it is multiplied by small h. So once you have this expression, then what you do? The remaining steps are very simple. Setting the first derivative of the total cost expression, is it okay? Assuming that this is the continuous the function, and that's why differentiable. So once you have the total cost expression, now what do? You differentiate with respect to the decision variable as a necessary condition. The optimal order quantity Q star is determined as these expressions you have. So you have an expression for Q star, and when you use this expression for the Q star, you get the expression for the optimal total cost. So this is the optimal total cost. So please you substitute, you have an expression for the total variable cost in terms of Q, and you substitute the expression of Q with these expressions. So ultimately you will get the optimal total cost expression. Okay. So this is a numerical example. So the manufacturing company has determined from an analysis of its accounting and production data for a certain part that its demand is 9,000 units per annum and is uniformly distributed over the year. That means the demand rate is uniform. Its cost price is ₹2 per unit. This is just an example. You go through this example, all the steps you follow. Its ordering cost is ₹40 per order. The inventory carrying charge is 9% of the inventory value, or say average inventory which you hold. Further, it's known that the lead time is uniform and equals 8 working days, and that the total working days in a year are 300. Determine the economic order quantity EOQ, the optimal number of orders per annum, the total ordering and holding cost associated with the policy of ordering an amount equal to EOQ, the reorder level you need to determine, the number of days stock at reorder level, the length of inventory cycle, the amount of savings that would be possible by switching to the policy of ordering EOQ determined in A from the present policy of ordering the requirements of this part thrice a year, and the increase in total cost associated with the ordering 20% more or 40% less than the EOQ. So these are the, all the solution steps are given. So please go through all the steps. Okay, all the details we have written. So these are the solutions. I am sure that I will be able to follow the steps. All the detailed calculations are given, and the kinds of the formulations or the expressions will be already expressions you are supposed to use to solve these problems. Obviously these expressions are already been derived and explained. So these are the solutions. Now this is the second numerical example. A contractor has to supply 10,000 paper cones per day to textile unit. He finds when he starts a production run, he can produce 25,000 paper cones per day. Is there another typical problem? The cost of holding a paper cone in stock for 1 year is 2 paise, and the setup cost of production run is ₹18. How frequently should the production run be made? Okay, so this is a typical problem. So here it is what you try to do. You try to determine that economic production quantity. So this is a problem related to economic production quantity, and that's why it is related to, this problem is related to self-supply case. So you have the expression for Q star, and you determine that the frequency of production run, that is the production run length, that is 9.5 days. So this way you solve the problem. Okay, so what is important is that you follow. So we have discussed what is EOQ, its application, what could be a typical the numerical the problem related to EOQ, and the second one that we have discussed, that is the self-supply case, that how to determine the economic production quantity. So all the steps we have explained, and we have also taken up one the typical numerical problem. So I hope that when you go through this the typical numerical problems, so your understanding will be better, and always I have explained the steps meticulously, point by point, so that you don't have any doubt. So all the steps you should follow. So thank you. So these are the textbooks.